Hey everyone. Today I want to talk about three concepts that I believe every Node.js developer should have in mind whenever they're writing code and they intend for it to scale well and be performant. For each of these concepts, we'll discuss them briefly and then jump into some code to see them in action. Feel free to skip around as you'd like. Now, if you're interested in learning more than this video, be sure to check out my Nest.js microservices course where you can learn how to build and deploy production-grade Node.js microservices. Okay, so I'm going to utilize Nest.js as a backend framework to review these Node.js concepts. Using Nest.js isn't mandatory. However, it's going to allow us to easily expose HTTP traffic in our application in a nice standardized way. So let's go ahead and get started. If you don't have the Nest CLI, you can simply install it using npm install-g nestjs/CLI, and you can get the latest. Now I have the Nest.js CLI. We can initialize a new project by using the nest new, and then we can give it a name. You can call it whatever you want. I'll call it Node.js concepts for this lecture, and I'll use pnpm as my package manager. So go ahead and let it finish installing some dependencies. So now that we've installed these dependencies, we'll simply cd into the Node.js concepts folder, and you can see here it's telling us we can run pnpm run start to start our server. Let's run pnpm run start dev, which is going to start the development server, and actually watch for changes and recompile if we change our code. So you can see our Nest app has successfully started. So let's go ahead and open up Postman so that we can try sending a sample request to this backend server before we go ahead and review the boilerplate code that's allowing this to work. Okay, so in Postman, I'll go ahead and launch a new GET request at HTTP localhost 3000, which is the default port for this Nest.js server, which we will soon see. So if you launch a GET request at it, you should see we have a hello world response coming back. Let's go ahead and take a look at the code inside of this server so we can understand it a little bit better. Okay, so this is a default Nest.js project. Importantly, in the source directory is where all of our code is going to live. We have this main.ts file, which is actually bootstrapping an application and creating our app with our root app module here. And it's also listening for HTTP traffic on port 3000, which is why we're able to send it GET requests. So we have that app module that we're importing. So in here we have a controller and a service that we're defining. So the controller is where we define our HTTP routes. So in this case, we have a GET route, and this is the hello world response that we sent back on that GET request. So if we go ahead and look at the app service get hello, which it's calling, we simply are returning this hello world string. So this is just the boilerplate Nest.js project out of the box. Now we're able to actually send HTTP traffic. Let's go ahead and dig deeper into some of these Node.js concepts that I want to review. Okay, so the first Node.js concept I want to review is the difference between blocking and non-blocking code in Node.js. So when we say blocking in Node.js, Node.js is single-threaded, right? It runs on a single thread. And so if we write code that is going to block this one thread, then Node.js won't be able to do any other work. It won't be able to respond to HTTP requests or do anything else if we're blocking that main thread. Now, the way Node.js is able to scale so well and handle so much I/O on this one thread is through the concept of the event loop. Now, you can think of the event loop as merely a way for us to specify what happens when an event occurs. So on the browser, you're very familiar with the concept of providing an on-event handler for when a user clicks a button, for example. Well, you can think of the event loop as something very similar. It's essentially a loop that's always running, checking to see if it needs to execute any of these callbacks that we define in our Node.js code. So the event loop is the reason why we're able to scale so much on a single thread. So you can think, for example, on a typical request, 95% of the time is going to be waiting for some database I/O to occur, where we're fetching data from a database, for example. Most of this time, we're simply waiting back from the database. And so the idea with Node.js is that we're not blocking that main thread while we're waiting. Instead, we've associated that database call with a callback. And once the network request completes, then Node.js will be able to execute that callback code again only when the database call is completed, so we're not blocking that main thread. And so this is actually very similar to how modern CPUs operate. A program is only going to run on the CPU for a specified amount of time, and then as soon as it needs to stop and wait for some I/O, like a network call, it gets kicked off of the CPU and won't come back on until it's ready to do more work. So this asynchronous model is exactly how Node.js is operating on a single thread. Now in other programming languages like C, Java, and so on, they handle concurrency by using separate threads. And this introduces additional complexity. Node.js, we only have this one single thread, and the event loop is constantly running, checking to see if it needs to execute any of the callbacks we've associated with asynchronous code that could be waiting for I/O. Now, if you're new to Node.js, this can sound like a lot to take in, and so that's why I'm going to leave some links in the description for some great articles to further understand how Node.js and the event loop actually works. So now that we have a brief overview of what the event loop actually is, I want to go back to review blocking versus non-blocking code. So blocking code in Node.js is going to be synchronous code that's essentially going to block that main Node.js thread, and it means the event loop isn't going to be able to run and check any additional callbacks in our asynchronous code. And what this means is we won't be able to actually do any more work while that blocking code is running. So let's take a closer look with some real code so we can actually understand what this looks like. All right, so back in our application, let's take a real world look at blocking versus non-blocking code in Node.js and see how we can make sure we're always not blocking this main thread so the event loop can constantly keep running and make sure our Node.js code is always scaling and performing well. Because if we have blocked that event loop, well, we're going to see the consequences of that really soon. So back in our app controller, let's go ahead and first create a new route in here. So we'll create a new get route, and I'll call this blocking. So this is going to be our blocking route where we implement some blocking code to see the effects of writing blocking code and what that looks like. So we're going to have a function called blocking. We'll call this, and I'll simply return this.appService.blocking. So we'll have to go on the app service and write a new function to actually implement this blocking code. All right, so let's start off with the function blocking. So it's important to note that Node.js is synchronous by default, and it's all happening in that one thread. So each line of code is going to be executed one after the other by default. And so that's going to be important to know in this blocking function. So let's go ahead and I want to create a while loop that's essentially going to run in perpetuity for a few seconds so we can see the effect of that. So to do that, I want to create a new variable called now, which will be the current date. So I want a new date.getTime. So this is the current time. And then I want to create a while loop here, right? That will have a new date.getTime. So while the current time is less than now plus, and this is the amount of time essentially we're going to run the loop for. So I want to go ahead and specify essentially 10,000 milliseconds, which is going to be 10 seconds. So I want to run this while loop for 10 seconds and show the effect of this on the Node.js runtime. And after this loop, we'll simply return an empty function. So let's go ahead and save our code and head back to Postman where we can go ahead and give this a try now. Okay, so back in Postman, we can go ahead and launch a request at the blocking route by targeting /blocking here and setting a get request there. Now, you can see the request is running right now, and it's going to take up to 10 seconds for that while loop to complete, and we should get a response back at the end. So you can see here it took 10 seconds and we got a response back. So out of the box, nothing looks bad here, right? We're just running some long running code and we do get a response back in the end. However, to see the effects of this blocking code, we want to launch a new GET request at localhost 3000. And we want to just target our hello world route. So if we just send a GET request, of course, we can see we get that hello world response back instantly. Now, what I want to do is I want to execute the blocking function, and then immediately you can see we tried to execute our get function, and you can see it's hanging. It's not returning hello world. then that's because our blocking code is running. As soon as the blocking call completes, then our get route for hello world will complete as well. And the reason for this is because this blocking call is blocking the one Node.js thread. It's not allowing the event loop to continue running and checking for additional callbacks. For example, the callback associated with this hello world request and response. This call is completely blocking our Node.js code. Now, something else I want to show you is if you go to a new terminal and you type in the top command, if you're using Linux or Mac, this will tell you the CPU usage of your applications. Now, I want to run the get route again for blocking and go ahead and look at your CPU. You can actually see our Node app, this is our Nest.js app here, is actually using the entire core associated with the app. It's using 100% CPU while this request is running. And that, again, is a consequence of writing this blocking code. When this blocking code is running, it's telling the CPU, hey, I need to run on the CPU. I'm executing some synchronous code, and I need to occupy the CPU time for this full 10 seconds my while loop is running. So it's getting scheduled on the CPU for 100% of the time here, you can see. And so there's no waiting. There's no asynchronous code that's happening. We're not executing something and telling the CPU, okay, I can wait a little bit, go do something else, and then come back to me. And that's why this code is blocking. It's hogging the entire thread that Node.js is assigned, and it's what we want to avoid when we're writing Node.js code. So let's go ahead and see how we can write an asynchronous version of this code so that we can tell the CPU, hey, I've done a little bit of work, but now you can go ahead and do other work while I'm waiting. So let's see how we can implement an asynchronous version of this sleep that we're doing here essentially. So let's create a new function, an asynchronous function called non-blocking. And we're going to do the same thing. We just want to wait 10 seconds. But now we're going to do it in an asynchronous way so we can free up the CPU and free up the thread for the event loop to continue running, process other requests in the meantime. So we're going to go ahead and return a new promise. And a promise in Node.js is really just syntactical sugar for callbacks. So we're going to be able to tell Node.js in the event loop, hey, here's some code that you can execute when I'm ready. So in this promise, we'll enter in an async function that has the resolve parameter, and that's where we can actually resolve the promise and tell Node.js, hey, we're ready to actually do something with a value. So in this case, I want to use set timeout, which is going to allow us to execute some code after an amount of time. So after 10 seconds, the same amount of time we're waiting in our blocking code, then I want to resolve this call and return. So now we've essentially transformed this blocking sleep into an asynchronous sleep where instead of performing this work synchronously, we're doing it asynchronously by returning a promise that will schedule this code to resolve in 10 seconds. And the big importance of this is that we don't block for this full 10 seconds. We free up Node.js to do other work while this promise is pending. So let's go ahead and prove this out by going back to our app controller, and now we can create a get route for non-blocking. So I'll call this non-blocking, and we'll call this async non-blocking, and we'll return this.appService.nonblocking. So let's go ahead and give it a try in Postman now. So now we'll change this route to be non-blocking, and we'll call it, and you can see it's running. And while it's running, we can go back to our other GET request and see how we're able to execute it and get response back while our non-blocking call is running. And so the reason that this works is because this non-blocking code isn't occupying the CPU time on the thread because it's asynchronous. We told Node.js, hey, we have this callback to execute. Whenever it's finished, then you can come back and execute my code. In the meantime, you can do other things. We can also go ahead and look at our CPU. And of course, Node.js isn't even registering on our CPU here because we're not doing any CPU intensive work while this is running. We do a little bit of setup and then we immediately free up the CPU to do other things while the promise is pending. So I hope this has shown you the difference between blocking and non-blocking code. Really, you can think of it on a high level. Synchronous code is going to be blocking, asynchronous code is non-blocking, and it's going to allow the CPU to do other things. It's going to allow the event loop to keep running. Okay, so the next concept I want to review is the idea of concurrency in Node.js. So as we've already reviewed, JavaScript execution in Node.js is single-threaded. So we're not going to have concurrency like we do in other languages like C or Java where we have multiple threads. Everything's in a single thread. So when we say concurrency, what we're talking about is the event loop's ability to execute callback functions after completing other work. So the way I like to think about it is less of concurrency and more about parallelism, or the ability to start multiple tasks at the same time, and then we let the event loop handle these tasks. And to achieve this parallelism, we're going to look at using promises. So let's go ahead and check it out. So back in our app controller, let's go ahead and create a new function first to demonstrate this code running in a non-parallel way. So we'll create a new get route and we'll call it promises. So I'll have an async promises function that will return this.appService.promises. All right, so let's go into the app service and I want to create a new async promises function. And in this function, I essentially want to loop over an array and do some asynchronous work with that array. So you can typically imagine in a Node.js app, you might have an array of values that you have to enrich by sending them to some external service. So typically you could loop over that array and send one request at a time. And so that's what I want to demonstrate in this function, is just executing one promise at a time and seeing the effect of that. So to do this, let's first start off by creating a results array where we're going to keep track of all of our results. Now I want to create a for loop that's going to start at 0. We're going to iterate 10 times and increment this I value each time. So now I want to actually execute some asynchronous code in this loop. So let's create a private async sleep function that's going to emulate some I/O. So it's essentially just going to sleep and wait for us. Now we want to do this in an asynchronous way, of course, so we don't block the event loop. So we'll simply return a new promise that has the resolve function. And I want to log something out at the start of this sleep. So to do this, I'll create a new private read-only logger at the top of our service. So this will be a new logger from Nest.js Common. And now I want to log something out at the beginning and say we are starting our sleep. And then I want to run a set timeout similar to what we've already done before. So after a second, we'll say our call took a second to reach some database or external service. Then we will log sleep complete. And we'll go ahead and resolve the promise with an empty object. So now we have this dummy I/O, right? So now we have this dummy I/O or sleep that's happening. We can actually use it in this loop. So we'll simply push to the results array and call await this.sleep. So we're awaiting this promise, and after its completion, we are pushing it to the results array, and we'll simply return the results back to the caller. But the key to this is that we're doing this one at a time. So each iteration, we're awaiting one promise at a time, and then at the end, we are returning our results array. So let's check out the effects of this if we go back to Postman and execute a GET request for promises. So if we go to our terminal and look at the logs, you can see this iteration. So we start the sleep, sleep completes, start sleep, sleep completes. And this is going to keep on going for each of our 10 iterations. It goes one at a time, starting, completing, pushing our result, and finally we return back our results array with 10 empty objects after 10 seconds. So this makes sense. But now what I want to show you is how we can actually execute these promises all at the same time and essentially wait until they all return. And once they all return, we can return immediately and make this call a lot faster because we execute all the promises in parallel. So we're telling the event loop, go ahead and execute all of them at once. So let's go ahead and see how we can do this by creating a new get route. We'll call this promises parallel, where we're going to execute multiple promises at once and see the effect of this. So call this promises parallel and return this.appService.promises parallel. And so let's go ahead and implement this function now. So we'll have the async promises parallel method. And so this is going to be very similar. So let's go ahead and copy the existing code from promises. However, the big difference here is now I don't want to await this call one at a time. So simply I want to push the promise itself to this results array, which I'll go ahead and rename to promises. So we're simply pushing the promise from the sleep method into this array. And then what we can do is we can use the promise.all function, which we can see here that will create a promise that is resolved within an array of results when all of the provided promises resolve or reject. So essentially what this is saying is it's going to wait until all of the promises in a provided array will resolve or reject, and then it'll return the return values from them all, which is exactly what we want. We want to execute all these promises at once and simply return as soon as they're all finished or they error out. So let's see the effect of running this code. We can go ahead and run the promises parallel function now, execute it, and see it's already completed. It only took a single second to run this. Now, if we look at our logs, you can get a really good idea of what's going on here. We have the start sleep log statement, but all 10 of them are executing at once here, and that's because we're starting all of these promises at once, right? We're not awaiting each of them like we were in the first loop. No, we're executing all of them at once. And so after we start the sleep, we wait a second, and then the event loop comes back around and sees, oh, I have a callback to now execute. And so it executes the callback after a second, and they all complete around the same time, which you can see here with the sleep complete log. So this way, we're not waiting for each promise individually. We're grouping them together and allowing them all to run at once and finish at once. Now, technically, this isn't happening at the same time. It's just happening very close together, since Node.js is happening all in one thread. And the event loop is essentially, again, it's running around in a loop, checking to see when these callbacks are ready. You can obviously see how much more performant this is when you have an array of promises, or essentially an array of asynchronous work to do, and you don't want to do that one promise at a time. You can group these promises together and execute them in parallel. It's going to speed things up a whole lot. Now, it's important to note that these promises do have some memory overhead in our application, so we want to be careful when we're executing an unbound array of promises and executing them all at once like this using promise.all. We want to make sure we're only executing this concurrently on a bound data set that we know won't overload our system. If we need a way to do this in a more controlled way, we have libraries that provide us a way to do this, like PQ, that I will leave a link to in the description if you're interested in checking out. All right, so the last concept I want to review is horizontal scaling in Node.js. So in Node.js, as we know from this lecture, is single-threaded. So we only have a single core to work with in one Node.js app. So what this means is if we need to use more than a single core of CPU, we need a way to actually scale horizontally in our application, which means running our application with multiple instances, and we can load balance requests between those different instances of the application. Now, of course, we do have ways to use multiple threads under the hood in Node.js now using worker threads. However, that does offer complexity along with it. So I want to review this horizontal scaling approach. Now, in order to first get a better look at this, I want to install a new package in our application that's going to allow us to do some load testing. So let's npm install save autocannon in our project, which is simply a CLI load testing tool that we can use to launch a lot of requests at our app. So in a new terminal window, I've gone ahead and entered this command, npm autocannon, which is going to execute autocannon. and then I want to execute it against localhost 3000/promises, which is our promises route. And then we have the -c for the number of concurrent requests we're making. So in this case, I'm launching 10,000 requests, which is obviously an insane number of requests to launch at our app. However, we're not doing a lot of work in our app. So if you were doing more CPU intensive work in your application, you obviously wouldn't need this amount of requests to reach 100% CPU. But in our case, we're not really doing a whole lot. So we're just going to launch a sheer number of large requests at it. This -t is going to make sure we don't stop for any timeouts that occur. And -d is the duration. So we'll go ahead and run it for 60 seconds. So I'll go ahead and run the autocannon command, which is going to go ahead and run our test against our API. And now you can see our logs are spitting out our promise generation. And if we go to top, we can see the node process is increasing in CPU usage. So you can see here we've gone up to about 60% and more. And of course, the kernel itself on my system is being maxed out because we're launching so many requests. And if we were to actually push this further, we would run into constraints. We wouldn't be able to push the CPU beyond 100% in our application. So we really want a way to be able to use more than 100% CPU in our Node app and scale it out. And to do that, we're going to use horizontal scaling, which means we're going to run multiple instances of our app and distribute those requests to each of the instances, and they can each use up a core. So to scale our application horizontally, we're going to take advantage of Docker and Kubernetes. So you want to make sure that you have Docker desktop on your system, and you also have Kubernetes enabled on it. So if you don't have Docker desktop or Kubernetes, I will leave a link in the description where you can download Docker desktop and actually get a Kubernetes cluster installed on it. All right, so to go ahead and get started, we first need to actually create a Docker file so we can Dockerize our app and build it into an image that we can then use and deploy in a Kubernetes cluster. So at the root of our project, I'll go ahead and create a new Docker file. So I've gone ahead and pasted in a basic two-stage Docker file here that's going to allow us to containerize the Nest.js app we've already built. Now, I'm not going to go in depth into this Docker file because I've done this in several other videos. So if you'd like to learn more about this Docker file and how we've actually built it, I'll leave a link in the description so you can check that video out. But essentially all you need to know is that these instructions will tell Docker how to actually build our code so it can be run inside of a container, which is what we want in Kubernetes. So we have this node command we're running after we've compiled all of our code to actually run the Node app. So now that we have the ability to build this Docker file, we want to actually deploy it somewhere so we can host the image and pull it in our Kubernetes cluster. Okay, so in my browser, I've gone to hub.docker.com, which is a repository where we can essentially host our Docker images. So go to this website if you want to create your own repository to host your image. You simply click on the Create Repository button and call it whatever you'd like. And you can see we have instructions here to actually tag the image and push the image. So you can go ahead and do this, or if you'd like, you can use the image that I've already created and pushed up here called Node.js Concepts. So let's go ahead and see how we tag and push this image to. So firstly, we're going to have to make sure we build this Docker image. So to do this, we're going to run Docker build and then give it a tag name. So the tag name here we'll call Node.js Concepts, and then the -f specifies the Docker file, and this dot here is where we're running it from. So this will be the root directory where we currently are. So you can see it's going to run through these steps to actually build our Docker file so that this code can be run and deployed in a container. So now that our Docker file is actually built, we're going to go ahead and run docker tag. And so docker tag is going to essentially rename this image, and then we want to enter here the name of the repository. So in this case, it's my username mguay22/Node.js Concepts, and then we give it a tag. So I'll give it the tag of latest, which will be the default tag. So now that we've tagged it, we can simply copy the name of the image that we tagged it to and run docker push to push the image to our repository. We're now actually ready to deploy this in Kubernetes locally so we can run multiple instances of this app. I want to firstly go to the root of our project, and I want to make a new directory called K8s, which is where we'll keep all of this Kubernetes code. So we'll cd into K8s, and now I want to use Helm. So if you don't have Helm, it allows us to essentially manage our Kubernetes cluster more easily and make it more portable. So if you don't have Helm, I'll leave a link in the description where you can grab it. Once you do have Helm, we can run helm create and then give it the name of the chart name. We're going to call it, this is going to create a new chart called Node.js Concepts. So we've created Node.js Concepts, and now if we go back to VS Code in our K8s folder, we can see it's created this Node.js Concepts folder for us with some default files. So this chart.yaml is going to describe the metadata for the chart. This values.yaml is simply values we can use to override the configuration of the chart, which we're not going to use, so we'll just delete everything. And then lastly, we'll just delete everything from inside the current templates folder. Now again, this isn't going to be an in-depth view of Helm or Kubernetes. If you want to learn more about that, I'll leave another link in the description where you can learn more from one of my other videos. For now, we simply want to create the minimum number of templates necessary to run our application and scale it horizontally. So to do this easily, we can go back to our terminal, and I want to cd into the Node.js Concepts folder and then into templates. So in here, I want to use Kubernetes to actually generate the YAML we need to deploy our application. So let's do this. We're going to run kubectl create deployment. So the deployment is the manifest for describing how to run our containers. So let's create a deployment called Node.js Concepts, and then we'll supply the image. So we know this image is going to be the Docker image we've already tagged. So we'll simply set this equal to mgway22/Node.js Concepts at latest, or you can use your repo if you've pushed this image up yourself. And then I want to specify the port option. So we specify we want a port exposed at 3000. And finally, we're going to set dry run equal to client and then output to YAML. And so this is going to make sure we don't actually create this deployment. It's simply going to output it to YAML. So we'll pipe this to a deployment.yaml file. And this will go ahead and create this deployment.yaml for us with everything we need to create this deployment. It's already filled out for us, which is excellent. So we can see here we have the container section where we have the image we're pulling, the port, and the name. So we know we're exposing our app on port 3000, which is just what we want. And by default, there's going to be one replica, so a single instance of this app. So now that we have the deployment, we also need to create a service. So a service is going to allow us to expose the deployment so we can send HTTP traffic to it, and it will be properly load balanced to all of the underlying instances. So to do this, we'll follow a similar pattern. We'll create a new service, and this is going to be a node port service. So a node port service is one that allows external traffic to enter into our Kubernetes cluster, and it's simply going to open up a port on the local machine that's running, which is exactly what we want. So we're going to go ahead and specify TCP, which is the port we want to expose. In our case, it's 3000, 3000. So this is going to be the node port and then the target port on the container, so we want to target port 3000. So we also want to give this a name. We'll call this Node.js Concepts. And then we'll, again, use dry run equal to client and output YAML and pipe this to a service.yaml file. So now we've created this template. If we go to the service.yaml, we can see here we've created a service, and the only thing we need to update here, so it looks like the name was incorrect. Let's name this Node.js Concepts. And now we have a service that is exposed on port 3000, and it's going to target port 3000 in our underlying container. And this key bit here is the selector. So we're going to select the app that has this app label Node.js Concepts. And this corresponds to our deployment, where if we scroll down here, we can see we apply this label to it, app Node.js concepts. So when we send requests to this node port service, it's automatically going to load balance it to any of the instances that have this selector, which is going to be the key to this horizontal scaling. So this is all we need to go ahead and get started. Let's go back to our terminal now, and we can cd into the root k8s folder. And now I want to run helm install. So how we actually deploy this Helm chart, and then we'll call it Node.js concepts to install it, and make sure we use dot here to specify the path, which in case is the current directory. So we can see here that it has been deployed. So we can run kubectl get pods to get the pods in our application, which are the instances of the app running in our deployment. So we can copy this pod name and run kubectl logs and output it. And we can see here that the app has started successfully, which is just what we want to see. Now importantly, if we also run kubectl get service, we can see the node port service that we created. And the key bit we want here is this node port. So this node port is how we're actually going to talk to this service. So this 301.02 node port will target the port 3000 on our app. So this port here is actually bound to our local machine. And so we can run a GET request at this node port on localhost, and we can execute the simple GET route and get back the hello world. So this is coming back from our Kubernetes cluster, which is excellent. Now what I want to do is actually scale up our deployment horizontally. So if I run kubectl get pods, we can run kubectl scale deployment, Node.js concepts, and specify the replicas to 5. And what this is going to do is it's going to simply scale our app up to now 5 running pods, and each of these pods is a new Node.js application that has a single core available to it when it's running. And so this is how we actually scale our Node.js app beyond a single core. We've now added new instances, and now when we send requests to the service, it will distribute these requests to these underlying pods and allow this compute to be scaled horizontally. Let's go ahead and actually run a test here to verify this. So if we go back to the terminal where we ran autocannon previously, we can go up until we find it, or use Control R to search for autocannon. Now I simply want to change the port here that we're targeting. So instead of localhost 3000 now, I want to target our node port. So I'll target 301.02 and execute this autocannon. Now you can see our test has gone ahead and started. And so now instead of running top, I want to run Docker stats to look at the stats of our Kubernetes pods. Since Docker is still running our Kubernetes pods underneath the hood, you can see as our test is running, the CPU usage of each pod has increased, and it's about even. And the reason for this is because we're sending requests to this node port service, and it's load balancing those requests to each available Node.js pod. So hopefully this demonstration of some core Node.js concepts has been useful for you. We've looked at how we can write non-blocking code and make sure we don't block the event loop, which is key to Node.js's scalability to thousands of concurrent requests at the same time. It all has to do with the idea of executing these asynchronous callbacks and not blocking the CPU or the only thread that Node.js has available to it. We've also looked at how we can execute multiple promises in parallel to increase our throughput. And finally, we've looked at how we can scale our application horizontally to take advantage of more than a single core in a Node.js app. So I really hope you've learned a lot in this video. Thanks so much for watching, and I'll see you in the next one.